So inverses cancel each other out, leave us with what we start with. So for instance, the cube root is the inverse function of the cube function. Notice if we were to put in the line y equals x, it creates a mirror between the function and its inverse. New function it's going to have a horizontal asymptote along the x-axis. It's going to have the point 0, 1. And it's called the exponential function. F of x equals b to the x. B cannot be 1. B greater than 0. This is the exponential function. The reason b, our base, can't be 1 is because 1 to any power is 1. It wouldn't look like this. It would be a horizontal line through 1. But let's imagine it was two to the x. And for x equals -2, -1, 0, 1, and 2, let's start with 0. Anything to the 0 power is 1. That's where we get our 0.01 that's always in the exponential function. 2 to the first is 2. 2 to the second is 4. 2 to the -1 is 1/2. 2 to the -2 is 1/4. So to the left of 0, negative numbers, we keep getting smaller and smaller fractions. 1/2, 1/4, 1/8, 1/16, 1/32. They get smaller and smaller and smaller, but they never reach 0. That's why this is a horizontal asymptote. To the right of 0, the positive numbers, they're going to get bigger and bigger more and more quickly. 2, 4, 8, 16, 32, 64. The larger the number we're putting in for the exponent, the even larger the y value. Exponential function. It has an inverse called the logarithmic function. This one has its asymptote on the vertical axis, the y-axis. Instead of always having its point at 0, 1, it'll always have its point at 1, 0. And it looks like this. Rises very steep to the left of 1, 0, but then grows extremely shallow as we move to the right. I said that they are inverses. Notice there's the logarithmic function. If I put the exponential function right over it, 0, 1 would have the point. Notice visually symmetric about the y equals x line, mirror image over this line. So visually we can see that they are inverses. But what exactly is a logarithm? Well, a logarithm is an exponent. Say it a couple times. A logarithm is an exponent. A logarithm is an exponent. A logarithm is an exponent. What do I mean by this? Well, let's say we have 2 to the third equals 8. This is a true exponential equation. The base is 2. The exponent is 3. So we can write an equivalent equation in logarithmic form. Log base 2, a logarithm is an exponent, and the argument of 8, the number that was left over that wasn't the base or the exponent, becomes the argument here. So the base 2 logarithm of 8 would be 3. A logarithm is an exponent. Logarithm is an exponent. So to evaluate a log, we look at the little base and we ask ourselves, what's the exponent that gives us this number? 2 to what power is 8? It would be 3. Four squared is 16. Base 4, exponent 2. So the base 4 logarithm of 16 is the exponent 2. 4 to what power is 16? 4 to the second power is 16. So these are saying the same thing. What would be the base 10 logarithm of 1,000? Well, base 10, the logarithm is the exponent, so that's what we're looking for. And it has to equal 1,000. 10 to what power is 1,000? 3. So since 10 cubed is 1,000, the base 10 log of 1,000 would be 3. There's always an understood number, no matter what we're doing in math. For instance, when we have the square root, we know that there's an invisible 2. If we have the number 10, we know that there's always an invisible 1 exponent on any number. If we just see the word log, this refers to the common logarithm, the common log. And that's base 10. So whenever we see log without a base written, we are to assume that the base is 10 because it's the common log. So what would be the log of 10? Well, the log of 10 would be the base 10 logarithm of 10. A logarithm is an exponent. 10 to what power is 10? 10 to the first. Because 10 to the first is 10. Let's write these log equations in exponential form. So here, this is the base 2 log. So in exponential form, the base is 2. A logarithm is an exponent. So the exponent is 4. And 2 to the 4th is 16. The argument, the number that's left. Log of 1 over 100 equals -2. We don't see a base. So what base is that? Base 10. The logarithm is an exponent. So the exponent is -2. 10 to the -2. The argument 1 over 100 is what's left. Base 7 log of 1 equals 0. The base is 7. A logarithm is an exponent, 0. Anything to the 0 power is 1. The argument is 1. So the log of 1 is always going to be 0 because 0 is the exponent that will raise any base to the number 1. Let's go the other way. 3 to the 4th is 81. Write it as a log expression. The logarithm is an exponent, so the log is going to be equal to the exponent of 4. Base is 3. That's our little number. The argument's 81. Ten to the 6th is 1 million. A logarithm is an exponent. So the log is going to be equal to 6. What's the base? The base is 10. We don't need to write it. That's just log. The argument is 1 million. Log of 1 million is 6. 6 is the exponent that raises the base 10 to the argument 1 million. One-fifth to the negative 1 equals 5. A logarithm is an exponent. The exponent's negative 1, so the log is equal to negative 1. What's the base on the log? The base is 1/5. Argument would be 5. Let's evaluate some of these. Log base 9 of 81. A logarithm is an exponent. What is the exponent that we raise 9 to give us 81? 9 squared is 81. 9 to the second power. If you can't think of it that way, then just put it in exponential form. The base is 9. The logarithm is an exponent, so we don't know what the exponent is, equaling the argument of 81. We know that 81 is 9 squared, so x is 2. The 1/2 base logarithm of 8 is what number? So ask yourself, 1/2 to what power is 8? This one might be a lot easier if we write it in exponential form. The base is 1/2. The logarithm is an exponent, so the exponent is unknown. This has to equal 8. Well, 8 is 2 to the third, which would be 1/2 to the negative third. So we see that x has to be negative 3. Then I introduced exponential and logarithmic functions. An exponential function, something like f of x equals some base to the power of x. And this will always have the 0.01 on it, because anything to the 0 power is 1. It'll always have 0, 1. And it has a horizontal asymptote on the x-axis. So exponential functions look like that. And actually, let me draw that a little better. Exponential rises steeply. This opposed to a logarithmic function, which is something like f of x equals a log of some base, the variable x. These are inverses. So since the point 0, 1 is always on exponential, the point 1, 0 is always on log. That means that the log of 1 is always 0. But 1, 0 is a point here. This one has a vertical asymptote on the y-axis. And it looks like this. Raises very steeply until it gets above the y-axis, and then it kind of slows down. Something to keep in mind about these is that just like any other function, we can move it up, down, left, or right. So let's say, for example, instead of this being b to the x, let's say it was 4 to the x. We can use our general shape, knowing that we have our horizontal asymptote at the x-axis and our always point of 0, 1 for exponential, to graph a new function. F of x equals 4 to the x plus 5 minus 2. Just like what we did at the beginning of the semester. Subtracting 2 from the function moves it down 2. So instead of the horizontal asymptote being here, it'll be down here. And x plus 5 adding to the x moves us left 5. So instead of our point at 0, 1, the point moves down 2, left 5. New graph looks like this. What would be the domain and range of the new graph? Well, from left to right, we'll always have x values. So the domain is all real numbers, negative infinity to infinity. But the range, negative infinity to positive infinity going up the y-axis. This graph doesn't have any y until it gets past -2, and then it'll have a y value forever. So that would be domain and range. All things we did earlier in the semester with other functions. Now we can also do those with the shape of an exponential function. Adding or subtracting to the entire function moves it up or down. Adding to the x moves us left, subtracting from the x moves us right. And then we look at domain and range, from negative infinity to positive infinity, left to right for domain, from negative infinity to positive infinity, bottom to top for range. So nothing new in the concepts, but we can apply it to our new functions. Same with a logarithmic function. We would take that shape. And pick it up, move it up, down, left, or right, depending on what the function tells us to do. Back into review. What is a logarithm? Remember, a logarithm is an exponent. And we can use this to go back and forth between log notation and exponential notation. For example, if we had log base 6 of 1 over 36 equals -2. The log is an exponent. The base is 6. So base 6 exponent -2 equals, well, the only thing that's left, the 1 over 36. And we know this is a true statement. And since that was a true statement, we'd hope to get something that's true. We can use that fact that a log is an exponent to rewrite it in exponential form. Remember, the base is the little number by the log. And if the log is an exponent, this log is -2. The exponent is -2. What about going in the other direction? If we have 5 to the -2 equals 1 over 25, base 5. So we would write log base 5. A logarithm is an exponent. The exponent is -2, so this log is -2. And what goes here? Well, the thing that's left, 1 over 25. So, a couple things to keep in mind. If we just have something like the log of 1,000 with no base written, recall that that is log base 10. So these are the same thing. When we don't see a base, that's base 10. There's another special type of log. And this one is shown as ln. So for instance, ln of 2. This is called the natural log. And this is the same as log base e. So these are the same thing. When we have a base e logarithm, that's the natural log that we write ln. And e is a special constant that's used in financial problems, continuous interest. E has a value of approximately 2.71828. And it goes on and on. So base E logarithms are natural logs, ln.